I'm Shane Campbell, Global Product Manager here at Donaldson Company. Today we're going to talk about edge cases for battery pack vents. So during this presentation, there'll be a brief overview of who we are as a company, why do you need to vent battery packs, and then get a little more technical, talking about what are edge cases, how do they affect battery enclosures, and how do we design around them. At the end of this presentation, there will be some time for Q&A. So Donaldson Company has been around for over 100 years, solving many different filtration problems. We were founded in 1915, but we've continued to grow in many diversified markets. We are located all around the world and have over 14,000 employees. At Donaldson, technology is our number one focus. We have over 100 technical centers where we are constantly looking at what new materials and filtration technologies can help solve our customer problems. So Donaldson is a diversified company. We have many different verticals focused for our end users. One advantage of this is that we can leverage technologies that are developed in one group for another group. And we constantly share this across the company and are always collaborating with each other. In addition to being diversified among many different businesses, our global presence allows us to leverage uh, world technologies from one region to another. We also have manufacturing locations and distribution centers located all over the world. So now our first topic today is automotive battery pack venting. The first question we need to answer is why vent battery packs? Well, in a battery pack, this is a sealed enclosure. And with a sealed enclosure, there can be changes in pressure from temperature and also elevation. So these pressure differentials without venting could lead to seal failure or deformation of the enclosure. So inside your battery pack, there's pressure changes, and the vent allows airflow to pass in and out of your battery pack. You can see here if there's over-pressurization inside your pack, the vent allows airflow to go out, and if there's under-pressurization, it allows airflow to come in. Also, a battery vent is a protective barrier against outside contaminants such as water, dust, and oil. So by putting a vent on your battery pack, it helps support your seal integrity and prevent leak paths into the battery pack. If you did not have a battery vent on your pack, you could get a vacuum or an overpressure condition, and this could cause a leak path past your O-ring or gasket into the pack. So there's a few different methods that are used to address battery pack venting. There are many single stage vents out there. You can see a breather vent, which is one of the stages. There's also burst and resealable options for the second stage of emergency degassing. But Donaldson is focused on delivering dual stage battery vents to the market that provide both breathing and emergency degassing. So there's two varieties of this. The first is a burst style vent, which we have our dual stage burst product, and then a resealable option, which is our dual stage flex. Uh, the core technology that really makes all of this possible is our ePTFE membrane. So at Donaldson, we developed this in-house with our proprietary Tetratex ePTFE. This membrane is oleophobic and hydrophobic. And because it's developed in-house, we are constantly looking at how can we improve this product and which formulation is best by optimizing pore size and other membrane properties to work in a dual stage battery vent. So with battery vents, there's four main functions of this product. The first is to seal and guard against external contaminants. Second is providing continuous pressure equalization, airflow in and out of your battery pack. And third is allowing effective ventilation to help prevent condensation inside your pack. The fourth function of a dual stage battery vent is to help ensure proper mitigation during thermal runaway and an emergency degassing event. There's that secondary function of the vent, which allows rapid degassing to get the heat and pressure out of your pack as fast as possible. So when designing a battery vent, there's many different considerations that we must consider. First being the functionality of the part, what inspection goes into the battery vent, but also the entire pack. What validation needs to be run on the part and also the pack level? What manufacturing steps are required to ensure we are creating a robust product? And then finally, the part needs to be designed for reliability. And a key piece of reliability is designing for edge cases. So the rest of the presentation, we'll get into what are edge cases and how do we design for them. Um, Shown here is just one of the many edge cases we'll get into, um, but this is our dual stage burst product and how it will burst during one edge case. So what exactly are edge cases? Well, to start off, normal driving, which is not an edge case, is stuff like tier one, tier two charging, um, maybe some mild mountain driving, your crosstown commute, or even a puddle splash with a little bit of water getting on your pack. Edge cases, however, are a bit more extreme. They are low occurrence events that will not happen day to day, but can happen over the lifetime of your vehicle and battery pack. So today we're going to talk about six different edge cases. The first is DC fast charging, a hill climb, water fording, air transportation, rock impact, and finally emergency degassing. Before we dive into these edge cases, just a little bit of housekeeping we need to do. Um, all of these edge cases are very specific to our setup used at Donaldson for testing, and each battery pack and vehicle will have different pressure, temperature, and edge cases unique to that application. Some of the assumptions that we're using here is 20 liters of free air volume within the battery pack enclosure, a temperature range between -40 and 80 degrees Celsius, an aircraft climb rate of 2,500 feet per minute, a Pikes Peak race time of 30 minutes, and timescale for all these events have been removed, but instead we're going to look at temperature and pressure. All right, so now we're going to dive into these six different edge cases and just give a brief overview of what they are, and then we'll follow up with some of the design considerations. So the first edge case is performance driving. And to paint a picture of scenarios where you might see these edge cases, let's pretend we're going on a vacation to the mountain region. So in the United States, maybe you're going to the Rocky Mountains in Colorado, or you're going to the Swiss Alps. So you land at your destination and you get your rental car and you're excited to get there and get to your hotel. So you hop in your vehicle and you get on the highway and start driving quickly. Well, during this, there will be an increase in both temperature, which causes an increase in pressure within your battery pack, as there's a lot of heat generated from the cells. The next step on your vacation, you get to a trail where you're going to do some off road driving. You rented a vehicle that's suited for this, so you're excited to push it to its limits. Well, you're driving along on this trail and you slip off a rock and you get an impact on the undercarriage of your vehicle. Well, this could cause a sudden spike in pressure that is due to the deformation of the battery pack. As the battery pack is impacted, this quickly changes the free air volume for one instance, but this in turn is a pressure spike that we'll see and the vent helps mitigate. So you're going along this trail, you've gotten through the rocky section, and now you come up to a river. Uh, you know that it's not too deep where you can still cross it, so you start making your way through the river. Well, your battery pack is hot from all the aggressive driving you've just done, and you submerge it into this cold river. Well, this thermal shock is going to cause a decrease in temperature, but also a decrease in pressure. So that is something that we must consider with a battery vent with these types of edge cases. So you finish your first day out on the trail and you uh, get back to your hotel and plug your vehicle into a DC fast charger. Well, during this charging event, there's going to be a rapid increase in your cell temperature and your battery pack temperature overall, and then this is also going to cause your pressure to increase with inside the battery pack. Next day of your vacation, you're well rested, and you want to see how fast you can climb up a mountain road. Um, so what you do is you start at the bottom, you step on the accelerator and try to race to the top of the mountain as fast as possible. Well, there's two things going on during this hill climb event. One is there's a lot of heat generated from those battery cells uh, from working the vehicle that hard. And second, there's going to be a change in altitude. Well, both of these factors are going to, um, one from the temperature and two from the altitude change, increase your pack pressure. And then finally, it's the end of your trip. Um, while it's not very realistic, let's say you decide to transport your vehicle back home. You liked it so much, you want to bring it with you. So you've figured out a way to transport this back home and bring it back by aircraft. There's also many subcomponents that will be shipped uh, via air transport during this type of edge case. So now your battery pack and the vent will experience a varied range of temperatures, but you will see both positive and negative pressures during takeoff and landing of the airplane. And with it a fully sealed battery pack, this will directly impact what you see inside the battery pack. And finally, the last edge case to include, this did not happen on your trip, thankfully, but if there were an emergency degassing event such as thermal runaway, um, we would see a very rapid increase in both temperature and pressure, and that is when the secondary function of a dual stage vent comes into play. So now let's talk a little bit about how do we design for these both at a system level, but also at a battery venting level. So we can group together the first four edge cases of performance, DC fast charging, hill climb, and air transport into some of the same considerations. So at a system level, we can minimize the free air volume to minimize the effects of temperature and pressure inside the pack. We can also increase cell cooling to help minimize those temperature changes, which then in turn will decrease uh, the changes we'll see in pack pressure. At a venting level, we can approach this at a few different ways. With a burst product, we can minimize these effects by having higher airflow. You can do that with higher permeability media or membrane. You can also increase the number of vents on your pack or just use larger vents to get more airflow. With a resealable option, we can use all the same considerations for higher airflow with the membrane and number and size of vents, or we can control the opening pressure of the vent so it can help relieve pressure during these edge cases. And here's the edge cases shown on the graph um, that we're referencing. So for rock impact, there are a lot of considerations that OEs are using to minimize the effects of this edge case. You can increase the battery enclosure stiffness with thicker materials, different cross-sectional geometries, or a different material. Another common approach is adding skid plates, especially if it is an off-road vehicle. From the venting perspective, it is important, especially with a burst style vent, to validate what is the max pressure that this vent can handle during testing to ensure that it will not prematurely burst. With a resealable vent, we can tune the opening pressure to, to understand if there is a sudden spike in pressure, the vent can help relieve that. And also, we have the option of using higher airflow, more vents, or higher permeability to relieve the pressure faster within the pack. This video shows uh, testing that we do in our lab for rock impact simulation. So there's a sudden increase in pressure, but what you can see is that the membrane does not hit the pins and it retains its functionality. So it will continue to seal and guard against contaminants, but still provide pressure equalization. All right, so when we look at the edge case of water fording, there are a few considerations at the system level. What type of materials are you using for the enclosure, and what's the thermal mass? Whether you're using metal, composites, or plastics, and also whether the enclosure is insulated, so it helps shelter from those sudden decreases in temperature, like we saw with that river crossing. From a venting perspective, you can help with this by having higher airflow, but also adding venting above the water fording line. Um, if the vent is below the water fording line, yes, it will protect against the ingress of water, but it will not be able to breathe because it is fully submerged. And then finally, for our last edge case of emergency degassing, there are many ways that venting helps with this. For burst style events, it is important to have high degassing airflow to get rid of the hot gas as fast as possible. It's also important to um, ensure that the vent stays open during the event so that there's nothing blocking um, the windows or ports on your battery vent to ensure continuous airflow during the emergency degassing. With a resealable battery vent, it is also important to have medium or high degassing airflow to get rid of the gas as fast as possible. But also with a resealable vent, we have the option of using a lower opening pressure to protect your pack sooner. Let's say the pack cannot withstand as high of pressures. Well, with the resealable option, it will open sooner and not allow the pack to experience those high pressures. Uh, with the resealable option, it is also very important to ensure that you have high airflow at a low delta pressure. Typically, airflow and delta pressure are proportional for most of the resealable options. So work with your battery vent provider to understand what is the airflow across all delta pressure ranges. This video here just shows what we do in our lab for burst testing of our dual stage burst product. You can see the graph on the bottom that pressure is ramped at a set rate, and then we measure what pressure will the vent burst at. And in this one, you see that the membrane completely rips open, providing a direct path for emergency degassing. So in conclusion, really the system level design impacts what the venting requirements are. What edge cases do you experience in your application? Where can we locate our vents on the pack? What's the material you're using for your battery pack enclosure? And even what's the surrounding structure? Are there skid plates on the vehicle? Where can we exhaust the gas through the battery vent? We encourage you to have conversations with your venting partner early in the design process. It helps us to better understand the application and find the right solution for you. And really, by developing with your venting partner, it enables system level optimization and finding the right solution for your application. So to reiterate, at Donaldson, we like to work with you early in the design process. We have expertise in ePTFE filtration that we can use to help find the right product or develop the right product with you. And then we like to work with you and learn along the process. That is how we've been able to understand a lot of these edge cases and use that information to improve our products. So we'd love to collaborate with you and find the perfect solution. So with that, we now will have some time for Q&A. Thank you.